Hello and welcome. Today, we are going to explore a fundamental concept in electronics and physics, the difference between signals that are in phase and out of phase. Understanding this is crucial for anyone learning about alternating current, or AC circuits, as well as waves in general. We'll break down everything you see in this image, step by step, so that it's perfectly clear. Let's begin with the first section at the top, labeled in phase. First, look at the graph on the left. This is a waveform diagram. The horizontal line in the middle represents 0, and it also represents the passage of time as we move from left to right. The vertical line on the left represents the value of a quantity, in this case, voltage. So, as the wave goes up, the voltage is positive, and as it goes down below the center line, the voltage is negative. On this graph, we see two waves, labeled V sub A and V sub B. Let's call them voltage A and voltage B for simplicity. These are sine waves, which are very common in AC electricity. Notice the behavior of these two waves. They both start at 0 at the exact same time. As time moves forward, they both rise together. Voltage A reaches a higher peak, meaning it has a larger amplitude or strength, but it reaches its peak at the exact same moment that voltage B reaches its lower peak. After peaking, they both start to decrease, and they cross the 0 line together, heading into the negative region. They both hit their lowest point, or their negative peak, at the same time. Then, they both rise back up and cross the 0 line again, all in perfect synchronization. When two waves follow this identical timing pattern, starting together, peaking together, and crossing 0 together, we say they are in phase. Think of it like two people rowing a boat in perfect unison. Their oars enter and leave the water at the exact same time. The fact that one person might be stronger and pull the oar with more force, like voltage A having a higher peak, doesn't change the fact that they are perfectly in sync. So, the text next to the graph that says V sub A and V sub B are in phase is simply stating this observation. They are locked together in time. Now, let's look at the diagram on the right, labeled figure phasor diagram. A phasor is a much simpler way to represent these waves. Instead of drawing the whole up and down wave, we can use a simple arrow, or vector. The length of the arrow represents the maximum value, or amplitude, of the wave. The direction the arrow points represents its phase, or its starting point in the cycle. In this phasor diagram, you see two arrows. The longer arrow is labeled V sub A, representing voltage A. The shorter arrow is labeled V sub B, for voltage B. Notice the most important thing here. Both arrows are pointing in the exact same direction. They are perfectly aligned. This alignment visually shows us that they are in phase. There is no angle between them. This leads us to the text above the phasor diagram, which says phi equals 0 radian. Let's break that down. The symbol that looks like a circle with a line through it is the Greek letter phi. In physics and electronics, phi is almost always used to represent the phase angle, which is the difference in timing between two waves. When the phase angle, phi, is equal to 0, it means there is absolutely no time difference between the waves. They are perfectly in phase. A radian is just a unit for measuring angles, like degrees. 0 radians is the same as 0 degrees. So, a phase angle of 0 means no separation, which is why the two phasor arrows point in the same direction. To summarize the first section, in phase means two waves are perfectly synchronized in time. On a waveform graph, they peak and cross 0 at the same moments. On a phasor diagram, their arrows point in the exact same direction, representing a phase angle difference of 0. Now, let's move on to the second section at the bottom, labeled out of phase. Again, let's start with the waveform graph on the left. We see two waves, voltage A and voltage B. Look closely at their relationship. At the very beginning, when voltage A is at its highest positive peak, look at where voltage B is. It's at its lowest negative peak. They are exact opposites. As time moves on, voltage A starts to decrease and crosses the 0 line. At that exact moment, voltage B is also crossing the 0 line, but it's going up. They are moving in opposite directions. When voltage A reaches its lowest negative peak, voltage B is now at its highest positive peak. They have completely swapped positions. This relationship, where one wave is the mirror image or the exact opposite of the other, is a special case called being perfectly out of phase, or in antiphase. Think of two people on a seesaw. When one person is at the highest point, the other is at the lowest point. They are perfectly out of sync. On this graph, you also see labels for V sub m. This stands for maximum voltage. It's showing that the peak positive value and the peak negative value have the same magnitude, or size. In this particular drawing, both voltage A and voltage B have the same amplitude, V sub m. The text next to the graph says V sub A and V sub B are out of phase. This describes the opposite relationship we just observed. Now, let's look at the corresponding phasor diagram on the right. Just like before, this is the simplified arrow representation. We have an arrow for voltage A pointing to the right. But now, look at the arrow for voltage B. It's pointing in the exact opposite direction, to the left. This visual opposition perfectly captures the seesaw relationship we saw in the waveform. They are on the same line but pointing in opposite directions. This brings us to the text above the phasor diagram, phi equals 180 degrees or pi. Let's decode this. Again, phi is the phase angle, the difference in timing. Here, it says the difference is 180 degrees. A full circle is 360 degrees, so 180 degrees is exactly half a circle. It represents a complete reversal of direction, which is why the arrows point away from each other. The text also says or pi. In angle measurement, 180 degrees is equivalent to a value called pi in radians. So, saying the phase difference is 180 degrees is the same as saying it's pi radians. This is the maximum possible phase difference between two waves. To summarize the second section, out of phase by 180 degrees means two waves are perfect opposites. When one is at its positive peak, the other is at its negative peak. On a phasor diagram, their arrows point in completely opposite directions, representing a phase angle difference of 180 degrees, or pi radians. So, in conclusion, phase is all about timing. In phase means perfect timing, a 0-degree difference. Out of phase means opposite timing, a 180-degree difference. These two cases represent the two extremes of how waves can relate to each other in time.